Dr. Mercedes Gimeno Segovia. She has done very interesting work in different areas of quantum information, quantum computing, one-way quantum computing, and photonics. And then it's a great pleasure to have her here. And today she's going to be talking about the TAD. Would you mind putting your slide?
Yes. Can you see them?
Yes, great. So therefore, so the talk will be about fault-tolerant quantum computing with photons, and also the first talk of tomorrow will be on a related topic by it's a Terry Rudolph. So I mean, this will be, I guess, coordinated, no, between. But if people miss one, can see the other one. You can see both. Is great because sometimes I need to see the same results twice or three times before I can connect the dots better. So it's a great pleasure to have you here.
Thank you.
Yeah, please go ahead.
Yeah, thank you. And yeah, as Franco said, yeah, Terry will be talking tomorrow, and our talks are on a similar topic, but with a little different focuses. So hopefully this will be of interest to everybody. Great. So I want to get it started. So roughly the outline of the talk, I want to give a little bit of motivation for fault tolerance and why we're focused on fault tolerant quantum computing architectures. Then I'm going to move on to discussing the computational model. So we use fusion-based quantum computation, which is a model that is slightly different from other models that exist, has similarities with measurement-based quantum computing, but it's certainly different. And then I will move on to its physical implementation. How do you actually build up the primitives and building blocks of that computational model using photonics? So I wanted to start with identifying fault tolerant as kind of one of the cornerstones of practical quantum computer architectures, because even though there is a lot of interest and a lot of research and work done in other architectures, really targeting fault tolerance means really thinking about the models that we use for building those architectures. And the reason that we're focused on fault tolerance is that it really does take 1 billion gates to do something useful. So what you see in the screen right now is a graph which plots the complexity of algorithms that are meant to be run on a quantum computer. So as a measure of complexity, we're simply using qubits times T gates. And on the bottom axis, we have date. So this is meant to represent the progress done on algorithm research across the entire field. This is an aggregate. You see all the papers listed below. Now, if you look at kind of the numbers of qubits and T gates that are necessary, you can see that it does take, even for something that if we have a machine with hundreds of logical qubits, it still takes more than 1 billion gates to do something useful. And there are different types of algorithms. Some require more, some less, but nonetheless, we do need a large number of gates. And so the question begs, well, how are we able to implement all those gates in a way that at the end of the computation, we can have any trust on the outcome, meaning that no error has occurred. So at this level, when we want to have, billions of gates, we're now talking about logical error rates of 10 to the minus 9, 10 to the minus 10. And in order to achieve that, we need to use error correction. So for error correction, we use our quantum error correcting codes that benefit from this threshold behavior. So hopefully everybody's familiar with this, but just as a quick reminder, so quantum error correction codes basically trade off the number of qubits for performance, but only if the raw performance, the raw error rate of those physical qubits is below a certain threshold. So here in this plot, you see you're seeing the scaling of the logical error rate as a function of some physical error rate. Now, this is just a simplified model to explain the concept. So you see here, we're plotting 3 lines. So they correspond to the same code. In this case, it was a Rasendorf lattice that we used to run this code. And you can see different, for different sizes of the code, you can see different performance with respect to its error rate. So if we are below threshold, making the code bigger means the error goes lower. Whereas if we are over the threshold, making the code bigger makes the error larger, right? So there's a hard limit where we want to be under for having a physical error rate. But once we're below that threshold, we should expect that making a larger machine with many physical qubits should enable us to achieve any logical error rate that we want to achieve. So this is what then, when designing architectures for quantum computing, really changes the way that you design some of those, because now you're no longer targeted at having a few good qubits. Now the target is having many qubits that are good enough to be below that threshold. And of course, achieving that threshold in itself is hard, but it's one has to focus on the scale and on the processing of all that data, as well as the interpretation of the results. Okay, so now I want to introduce fusion-based quantum computing. So fusion-based quantum computing is basically a new fault-tolerant framework for quantum computation. I mean, it's actually generally applicable to matter-based qubits, but it's really ideal for linear optical quantum computing, and that's the context in which it was developed. So the primitives of the fault-tolerant of this new fault-tolerant framework is, well, first we start with resource states. So resource states are small entangled states of a few qubits. They are usually can be represented as stabilizer states, since they are the basis of most quantum error correcting codes. And the fact that they are small mean that their errors are going to be low in comparison to the preparation of very large states, because the errors are going to be bounded by the size of the resource state. And the other primitive are projective entangling measurements. So these are measurements that they're equivalent to doing a 2-qubit gate followed by a couple of measurements, and they usually are used to extract correlations like Bell type correlations, XX, etc. And we can always failures of these measurements are going to be, well, Pauli error. So we have a bit flip in one of our correlations, or flip in one of our correlations, or we can have erasure, which means that we have lost the value of at least one of those correlations. And then these primitives are structured in what we call a fusion network. This is simply a recipe for how are we going to do these projective entangling measurements on the resource states themselves. And one of the things that is crucial in this, in fusion-based quantum computing, and the reason why is an inherently fault-tolerant framework, is that the design of the fusion network is such that the correlations are structured in the same way as some specific topological code. So for example, we could have a torical version of the fusion network, a kind of a Rasendorf version, a color code version. There's ways of making any error correcting code by simply structuring the fusion network and the fusion measurements in the right way. And so this is, as I say, is one of the main differences with respect to this, of this framework with respect to all others. But I think it actually helps to identify mainly the differences with MBQC. I mean, they share the last 3 letters, so they tend to be associated. So these are the 3 main differences that we can identify. So, well, just to start with the kind of this resource state, we have that in MBQC, the size of the resource state is actually dependent on the algorithm. Longer algorithms require longer cluster states to have been generated, whereas in FBQC, the size of the resource state is independent of the algorithm, which means that the same hardware and the same hardware and architecture can be used for multiple multiple algorithms. One of the main differences, as well as a measurement, MBQC has single qubit measurements, whereas in FBQC there are 2 qubit measurements. And the last one, fault tolerance, which is, as I said, is integrated in the design of the fusion network in the case of fusion-based quantum computing, whereas it's completely independent of the cluster state generation, and it has to be an add-on that is put on top of the cluster state that we have already generated. So to give an example, in looking at this kind of an FBQC scheme, like what are the primitives, a network and decoding scheme. So for example, we can start with a resource state that is 6 qubits configured in this ring configuration. And here I'm using the usual convention of the circles represents qubits, the lines or the edges represent entanglement between those qubits, and the resource states we usually, I mean, any other resource state could be generated. Here we focus on states that are stabilizer states because they are the basis for most quantum error correcting codes known. So here you have both the pictorial as well as the stabilizer representation. And fusion is in this case just a simple Bell measurement with 2 outcomes, the correlations of the X and the Z operators. So the network is defined in terms of a unit cell. So in this case, the unit cell is composed of 2 of these resource states, the ones that are in kind of in purple, these kind of hexagons that are at the corners of the unit cell, and as well as the fusions between those qubits and other qubits from other cells. And one should imagine that the cells are basically tiled in order to form a fabric, so to speak, from which the correlations are extracted. So this is kind of similar to when we imagined Tori code implemented in superconducting qubits, where we have kind of physical, like spatially separated qubits that then we have two qubit gates being applied. So here's very similar, except that we are always assuming that these operations are destructive. Sorry, they're destructive. Okay. And then the decoding scheme. So it's not enough to have quantum states and some quantum measurements, but those, as I said, like they correspond to an error correcting codes, and we need to be able to decode them. We need to be able to interpret them. So they go as we, at the same time as defining the network, we also define the decoding scheme. Here, for example, I am showing a syndrome graph that is basically used to decode a fusion network like this one. Now, so far I've been talking about error correction, but in order to do computation, we need to do logic. And in order to do logic, what we can do is basically implement topological features, which means, for example, adding boundaries by changing the way that we're measuring some qubits, or even defects in the lattice, right? So you can imagine a perfect lattice. I would be implementing an identity gate, and now once I start adding some boundaries, some defects, I can start adding some other logic. And there's a paper by a number of my colleagues recently on the archive where they basically go into a lot of detail discussing what are those logical blocks that we can use for fault-tolerant quantum computation. And so this, for example, is showing you an example of I think this is a part of a magic state distillation protocol, one of the 3-qubit gates of the 15.1 magic state distillation. And you can see here, this is showing a syndrome graph, which means like each of one of those lines like that are kind of grayed out is one measurement. And the measurements are structured in such a way that the boundaries blue and red here determine how, like, there's a measurement that is done there that is to terminate some membranes, and the membranes that I'm referring to are these edges that are seen in blue. So the combination of all the measurements that are part of that membrane is now interpreted to determine the value of a logical operator. Okay, so just to zoom out a little bit, we've been talking about fusion networks, and there's 2 things about fusion networks that should be clear. The fusion network, I can look at two things. I can look at the microscopic features, exactly what are the resource states, what are the fusions, how are they arranged, how are they put together. That gives me an understanding of the error correction properties of that fusion network. And now the kind of macroscopic features, like the larger defects, like almost as if you consider this a piece of material, all of those macroscopic features actually tell me something about the use or the operation that that fusion network can be implemented if I decode it correctly. So, for example, here I'm showing, I think this was a skate, but yeah, so you can see the different features. And just to make an analogy, it's almost as if we looked at, like the fusion network is like your raw material, and it's the chemical structure of that raw material is what it gives it its strength, and the same way as the microscopic features of the fusion network is what gives the error correcting properties. But what you do with it, like you can malleably change a lot of the features, like macroscopic features, by doing certain measurements in a different way, and that allows you to actually have a lot of flexibility to do operations. So now that I've introduced FBUC, let me move on to how do we implement this with photonics. So why focus on photons? There's a lot of very nice properties. For example, they have a fast measurement and clock speed. Now, this is very interesting because having nanosecond latencies and very fast clock rates allows you to do many gates in a short amount of time. Because even if you have the best error correcting code, if it takes a minute to run every gate, there's no way that you're going to be able to run billions of them in some realistic human lifetime. The other nice thing about photons, there's not really quantum crosstalk across them. The only noise that they see is basically lost if they get absorbed into material, or if there's any problem with the control that you are applying in order to make them do certain operation, and that is much more controllable. And the other nice feature is that they're not geometrically constrained, meaning that we can look at all sorts of topologically interesting but maybe non-local codes and look at how to implement them, because our qubits are not fixed in one point in space, right? And not only do we compute with photons, in particular, we use dual rail qubits. So this means that our qubits are encoded in two modes. Like a single qubit has two modes. A single qubit has one photon in two modes. It's either spatial or polarization or path or time. There's many options. And the reason that we're focused on that is that we have losses heralded. So basically the encoding of the photons into qubits is already acting as a small error detecting code, detecting the type of error that is most common for photons. There's very clean linear optical operations, etc. And dual rail qubits are really, they act as like the first layer of error detecting this encoding. And finally, why do we look at silicon photonics in particular? It has many advantages, but one of the main ones is that it has operating temperatures that are hundreds of times higher than other platforms, in particular superconducting qubits. And the reason this is important is that when we look at, it's again scale, right? Like at the beginning, I showed you, well, if we want to do something that is useful, it has to have billions of gates. If I need to do billions of gates, I need to have encoding, like I have to have fault tolerance. But fault tolerance comes not only with quality of the raw material, but also with the scale. I need to make, the bigger I make my logical qubit in terms of physical qubits, the more I can suppress my logical error rate. So then considering scale becomes very important, because not only do you have to have a scalable control electronics that can track all of that, but when you start looking at what is the cooling power required in order to maintain and operate this machine, then you can see how going up to like the few Kelvin regime, which is where we're operating at, really gives a huge advantage. Now, I want to address the common comment in terms of, you know, the elephant in the room, as I'm showing here, with respect to photons, which is, well, but you can only generate entanglement in a probabilistically. Now, first of all, that is not completely accurate, because entanglement generation with photons is only probabilistic in the dual rail encoding. If I was using single rail encoding, entanglement would be deterministic. Now, the reason, so, well, it's not a reason, but it's a price that we are paying. And the price that we're paying is because we want to have that first level of loss detection that is essential, given that loss is the biggest contributor to noise or error in our computer. Now, one thing to note is that even though loss is the most common type of error, and in fact it's, you know, it's a predominant, error correcting codes that, I mean, I'm not citing here, but some of my colleagues, Naomi Nickerson and Hector Bombin, had some papers a few years back showing that we can tolerate about 10 times more loss than Pauli error, because loss is a heralded error. So we know, we don't know, we cannot recover what information was there, but we know that the error has happened, right? And that proves extremely useful and actually pushes the threshold high quite a lot. So in terms of entanglement, yes, it is true that with dual rail encoding, we only have probabilistic entanglement. However, we are not, this is not the case that you have a probabilistic operation and then you have to get them all to succeed. We have the ability to select successful events to reduce the number of resources. And actually, this is what leads to the polynomial scaling of the first proposal for optical quantum computing from Neil Laflamme and Milgram back in 2001. So this idea that being able to select successful events instead of having this compounding of probability is really enables you to have a scalable quantum computer. But now, of course, when we talk about this scalable, we just talk about polynomial scaling. You really care about, well, but what is the constant, what is the overhead on the of that scaling? And for FEQC is constant and is small. Okay, so looking at the primitives that we have for fusion-based quantum computing, so we need, for resource states, we need sources of single photons. We need projective entangling operations. So this means interferometers and detectors, and as well as the ability to do switch networks, which it means also interferometers, but with active phase shifters that we can control. So the manipulation of single photons can be done very simply. This is, for example, is showing you a Mach-Zehnder interferometer that allows you to prepare any single qubit state. Through, you know, we have two beam splitters that are implemented through directional couplers, where we have two waveguides that come very close together, such that the mode going through one of them can be can evanescently couple on the other one, as well as we can have phase shifters. There's many technologies to apply phase shifters, from thermal, apply thermal tuners, where we apply some heat so that we change the properties of the material underneath, to some other electro-optical materials that are faster. So there's kind of a number of options there. The fusion gates that I've spoken at the beginning are actually a primitive, are a fundamental gate for optics, and they could not get simpler. They're simply a beam splitter followed by a measurement. Now here I'm showing an example where I take two entangled states, I apply a fusion gate. If the gate fails, then I will find myself with having destroyed or like measured out those two qubits, so that I have now less entanglement than I had before. And if I succeed, however, now I have created a lot more entanglement. And what is crucial is that, and this is across the entire, anything that I'm going to talk about, any measurement, any generation, like we always have a signature of what has happened. Whenever there's one of these probabilistic operations, the detection outcomes tell us whether we succeeded or failed. So for example, in this case, success would be heralded by measuring a single photon on one of the two detectors here, whereas failure would be heralded by having either two photons on one detector, or one photon in both detectors, or no photons in any of the detectors. So the generation of entangled state is done through the same protocol. So Notice here, this entangling gate is done through interference and measurement. Here, the generation of entangled states from single photons is also done through interference and then measurement. This is what is often referred to as measurement-induced nonlinearity. And so we can go using the same protocols from single photons to some larger states or smaller states, for example, belt states or GIZ states. Now we can take groups of those GIZ states, apply fusions to them, and obtain another resource state that has more interesting or relevant entanglement structure. And it's worth noting that even though each step is probabilistic, we are able to select the successful events and push them forward. So you pay a price, a constant overhead per resource state, because you have to, you have to account for the number of times that you're going to fail in the preparation. However, that is a constant overhead for a fixed resource site. And so here I wanted to just simply mention a couple of papers that we have where a lot of the operations and methods that were known in the literature before, there's a lot of opportunities to improve them. So for example, in terms of the creation of entangled states using linear optics, the previous best success probability of how to turn 4 single photons into a belt state was actually 25%, and we found through a number of methods that you can boost it up all the way up to 66%, as well as, for example, making the fusion. So fusion usually works with about 50% probability, and you can use single photons to boost that probability for over 50%. And we also looked at efficient switch networks for linear optical quantum computing. So this means how are like the element that allows you to select out of all of those options that you have successfully generated. It allows you to select out which one is the one that you want to operate on at the next step. And one of the things that we found was previously, in order to do many routing, in order to be able to extract all of the different states that have succeeded, as well as doing any temporal multiplexing, which means that it allows you to use a single piece of hardware repeated multiple times with generation of multiple time steps in order to kind of feed a next step. All of those things were previously known to have logarithmic depth in the number of phase shifters. The reason you don't want to do this is that logarithmic depth actually means that the larger your computer is, the more cost or the more error you're adding, which is something that doesn't play so well with wanting to remain under a certain threshold. But we found that there's constant depth for both of those cases, basically allowing us to kind of cap the amount of error that any of these operations are going to generate. And so when we talk about the generation of resource states and then a fusion network, I mean, so far I only talked about the resource states. And so you can imagine, so this is a kind of a GIF that that we have to kind of represent what the computation might look like. So you're generating layers of resource states, right? That and then you're fusing them. So here the red hexagons are the resource states. The yellow lines represent fusions. And note that after each fusion, now that we are left with is some classical data that is some classical data that is used to basically they carries the correlations that we're obtaining out of this fusion graph. So you can imagine that the computation is, remember we were generating this fusion graph blocks, right? Almost like that then we can carve out into different shapes to do logic. So this is kind of one of those baselines. And so one of the things that we found was that we can use optical fiber in order to boost our ability to do this without requiring to increase the size of our machine. And the reason is that optical fiber is key for photonics. It's a very well-known technology, has been developed for many years. And one of the crucial things to note about our architecture is that it doesn't require a quantum memory in the sense of a kind of a random access. I can obtain information at any time. We only required fixed delays, for which optical fiber is an excellent memory. So we can use, like, in order to do a lot of computation, we can keep some of our qubits alive through optical fiber, in order to be able to do computation with them at basically, I mean, obviously, if you put like many kilometers of fiber, you're going to have some loss, but it really the amount of error that it adds is very small for the amount of utility that it gives. And so one of the ways in which we use this fiber is to basically have, you know, here I'm attempting to generate the same level of fusion graph, but instead of having one by one, like layer by layer, the generation, now I have a single generator that is basically generating this entire lattice. And basically I have reduced the amount of resources required by a factor of d squared, with d is like, you know, some value from like about 10 to possibly 40. And so this is a few, I've kind of notched out a couple of orders of magnitude of that constant overhead that I was discussing earlier. And this is actually something that is uniquely, you know, because it's uniquely useful in photonics, as well as photonics is uniquely capable of doing it, simply because photons are, they don't need to be assigned to a specific location in space, but they have this kind of reconfigurable geometry. And in fact, so this is another paper that we published recently, where my colleagues go over a number of different schemes where you're using interleaving. So in order to do that kind of that using a single resource state to kind of fill out all of this fusion graph, basically you can imagine it as having like some generation of a resource, and then some qubits are delayed by certain different amounts in order to be able to be fused with photons that come from resource state generated a bit later or a bit earlier. And the other capability that this interleaving framework gives us is actually to implement a huge number of error correcting codes that have non-local properties, as well as kind of like geometries that are not so amenable to having kind of a flat type of architecture. So, like, so to speak, imagine if you had a single, you know, if you have a grid and you can only do things with a specific grid. If you start with a rectangular grid, it's actually very wasteful to try to make any other underlying geometry. Whereas here, basically, we go on to having the opportunity of not having that baseline geometry and accessing other different types of codes. So with this, I wanna finish. This was almost a bit of a tour de force over a lot of the, you know, the kind of the motivation and the thinking behind some of our choices, as well as some details on the areas where we have been working to improve the schemes that we have. And so here I've mentioned a number of papers that we have published, and so I wanted to have them listed here for easy access. These are all the archive links. And with this, I would like to thank you all for listening, and thank you to the organizers for giving me the opportunity of telling you a little bit about the work that we do. Thank you.
Thank you very much. Thank you for the great talk. And then I'm wondering, if you show slide 29, you were showing the fusion gates replacing CNOT gates. It is possible to do it for ISWAP gates, because some algorithms, people have found that you can get them faster moving forward, not focusing on the CNOT gates, but ISWAP. The other question is that in the next slide, you're showing about how to generate GSD state. Can you do W states? And there are some other questions like relation to lattice surgery and some other questions that I can ask you afterwards.
Sure. So I guess, yeah, in terms of like the specific gate that we're using, I mean, here we're using one specific fusion gate. There's actually multiple, like, I mean, I'm here showing one example because it's the simplest, but we actually consider a number, like fusion gates for photons. They can be like, you know, like there's a traditional type 1 and type 2. You can also fuse more qubits like that to generate entanglement across more states. That comes with some trade-offs on probability and error, etc. So the the most fundamental thing about FBQC is not that you use a CNOT gate, and it's not that you generate specifically a G8-set state or something else. The most fundamental thing is that we have at the baseline, what we're trying to generate is really a let me go here. Like, what we're trying to generate is a fusion network that has error correcting properties. That then I can take some of that, I can take the outcomes of operations there, and they correspond to a measure, to correlations that I can then decode and use for information, right? So the main difference is not that I configure some physical structure and then I have to figure out how to turn it into like an error correcting code, but that fundamentally that design is there. And so there are multiple resource states that can be used. In fact, this is one area where we actively look for what are the ones that give us the best cost benefit, as well as multiple different fusion operations and fusion networks that can enable different aspects. So it's yeah, it's, I mean, of course, that depends on depending on the physical, you know, what are the gates that are physically more possible or easier to implement. Then there might be different schemes, but this is fundamentally it's a framework, right? In the same way as, you know, circuit-based or measurement-based quantum computing doesn't tell you exactly which are the only gates one should use, but simply that the difference is in circuit-based quantum computing, we have a number of qubits and we sequentially apply gates to them. Some of those gates are entangling gates. Some of the time we apply measurements. MBQC is we prepare a state that has, you know, correlations of all the entanglement is there, and we only do computation by doing single qubit measurement and then feed forwarding information. Fusion-based is the concept is we take small resource states and we apply entangling operations as well as single qubit measurements. So it's basically a framework and can be applied to many different individual details that are more applicable to any physical system.
Thank you very much. A quick question: when you look at your preparing creation of entangled photonic state using linear optics, the one like you show with Sara Bartolucci et al., the Bell pairs generation from single photons appear with probability 66%. Is that high enough, or because I thought you might wanted to bring this like to something like 4 nines or 3 nines or at least 2 nines? Isn't this like too low? Or
so this is the fundamental rate. With the fundamental rate, so this means that every time I try, I get 66% chance. And so if I, like, you can calculate if I have 2 goes or if I have 3 goes, what would be my chances? And I mean, I have to say, even in cases where you have, you know, even the original, you know, in the original, to prepare 3 G8 sets, you need something like you have like 3% probability. This is the baseline that is in the literature, right? Even if I take that one and I just have you know, something like about 50 copies of that attempt, and those 50 copies can be spatially separated or can be temporally separated, which means that the same generator attempts a number of times. I'm storing the you know, the different attempts in fiber, and then I am able to switch the one that I want. Like, that should be enough, right? Like, this is where the small constant overhead comes from, that for the generation of a Bell pair, I actually have to take to generate a number of them before I can actually use them. Now, another interesting thing I think that maybe is not so realized is that we don't need 99.99% on the generation or even on the success of our gates. And the reason for that is that one can realize that our error correcting code, because it has the ability to correct for erasure, then we need to understand how to encode failure of the generation of entanglement or the generation of a particular resource state can be also treated as failure or erasure of certain correlations we were expecting to get for the code. So at some level, it doesn't make any more sense to burn resources in trying to make the probability higher, because our error correcting code will be able to cope with the erasure of those correlations that would have been generated if I had the success. So this is actually an interesting point where, you know, exactly how much do you put on the error correcting code versus how much are you physically trying to boost up your probabilities. It's an optimization that really depends on carefully analyzing, you know, what other kinds of errors do you have? What are your abilities to generate to resolve them, and it really like requires you to understand clearly the implementation to be able to make that trade-off.
Oh, thanks. There is a question in the chat from Christian Aime Nejuem. He say, thanks for the nice talk. Please, on what are based microscopic features in comparison of macroscopic features?
I see. So yeah, so the way to think about it is microscopic features is what acts on single physical qubits, so single photons. So a microscopic feature would be the difference between I have a photon from a resource state and I decide to which other photon from which other resource state is it entangled with, or which measurement am I applying. Now, macroscopic features is something that you can only see when you kind of zoom out and look at a number of photons or a number of resource states that are now fused into a fusion graph, and then you decide for this bulk of fusion graph, I'm gonna look at a defect that might be a dislocation. So this almost like it actually helps a lot to think of it as almost like as a crystallographic structure, where you can think about, well, if I look really close in, I can see, oh, this atom is you know, has like van der Waals interaction with this one, is in the same molecule as that other one. That is the microscopic feature, which in our case corresponds to which qubit is part of which resource state, which fusion, etc. Macroscopic just means, oh, I can see a dislocation in the crystallographic lattice, which actually that kind of dislocation is a defect that we use to do computation. So in that paper, the photon logic one is covered. So they are these kind of emergent properties that can only be seen once you consider ensembles of resource states and fusions, and not at the single fusion, single resource state level.
Oh, thanks. Yeah, Omololu, you have a question?
Hello? Yes. Thank you very much for the talk. I have a more practical question. So I assume you already have a quantum computer built from this work that you are showing us. And like, how many qubits are you able to put together?
So yeah, so we are currently in development. So it's in terms of, so for qubits depends on whether we are talking about so we don't currently have any logical qubits, and for us all of our intermediate milestones are to build out the systems required to support those. So in that sense, I cannot say, yeah, we don't have any logical qubits, and we also are not currently working on milestones that would have a small number of qubits that can be used in the NISQ regime. So at the moment, in order, as I said earlier, when you think of fault tolerance, it requires the development of large-scale infrastructure, control electronics, cryogenics that would be able to support that. So we are in the kind of concurrent development. We have very, you know, at the single qubit level and like at the small gates, we have very good fidelity in the platforms that we're using. We are also developing in parallel our ability to scale some of those properties. And I mean, at the moment, our target basically is that by mid of the decade, we'll have kind of all the manufacturing processes needed in order to enable large scale production. And this is a kind of similar to, you know, we are currently producing a lot of our chips in global foundries, which is a tier 1 fab, say that produces the same chips as computers and mobile phones, etc. So it's a little bit of a different process, because it's not a process where we build an experimental setup and then a scale given those technologies. We're trying to make a leap where, like, at the very beginning it's going to be slower to show some of those like qubit numbers, but then the scaling will be there, and we will be able to rapidly go on to showing that.
Okay, thank you very much. Any questions from the audience in Kigali? Okay. Yeah, thanks. There's a question in the chat. What is the projected speed of the quantum computer in the future? I think this is a question for Franco.
So is that question for Franco?
Oh,
Yeah,
here
because
it is.
it's a general question. Yeah, Franco can read it.
No, but let me ask, we have Mercedes speaking now. So the question in the chat, which appeared like right now, like a minute ago, what is the projected speed of this quantum computer in the future? So I think it is asking about the computer inside quantum. So therefore, will be the speed comparable to superconducting qubits, or I mean, ion traps will be slower, but I guess how will it compare, or are there any estimates or ballpark or guesses or?
Okay, so the answer I am able to give, and again, I also want to note that I'm not an expert on other technologies. So what fundamentally is gonna block the speed of operation in a computer is not only, so we have two elements. One of them is our ability to perform physical operations. Physical operations for our photons, again, they're like latencies are nanoseconds. The actual operations are picosecond, hundreds of picosecond operations. So for photons, it all comes down to how much of this time-space trade-off are you willing to make. Whenever you trade space for time, you're basically making your operations longer. On the other hand, we have the constraint of how fast can your control electronics be, right? So in some architectures, on some platforms, the classical control electronics are actually not a problem, not a bottleneck, because your qubit operations are much slower. That is not the case for us. For us, our qubit operations are the single qubit operation much faster than control electronics. So ultimately, some of when we discuss with our electronics team, we're really at the border. Like we need really high performing electronics to be able to operate. And then not only just kind of a single level control, but then there's also the fact that decoding is a hard problem. I mean, there's a number of decoders, like some of my colleagues have developed linear time decoding algorithms to run. We've actually benchmarked those, and in the amount of time that it takes to resolve some of those decoding problems, actually it's perfectly matched to the timing. So I mean, I've given a very round answer without giving you a number. I think one should consider that operations for our qubits are in the order of picoseconds, and we expect to be in the order of kind of hundreds of nanoseconds, possibly a little bit more, for logical operations.
Oh, thank you.